Good afternoon. So today is our 13th lecture, and now slowly we will start entering into the analysis of fluid particles present in the surrounding fluid mediums. Okay, and today particularly we will try to see two different flow situations. One is potential flow, and another is slow viscous flow past spheres. And whenever I am talking about the spheres, I am considering that the shape of the particles is spherical. It can be a solid particle or it can be a fluid particle. Okay, so before going to this analysis, first quickly I will recapitulate the concepts of stream function and vorticity. First, why we want to study these concepts? Because whenever I will be talking about the flow past spheres, I will be taking the advantage of axis symmetry. Okay, so once I am considering the advantage of axis symmetry, by that axis symmetric situations, actually our flow phenomenon becomes two-dimensional. Okay, so once we have a two-dimensional flow phenomenon, then instead of solving the complete set of continuity and momentum equations, of course we will be solving complete set of continuity and momentum equations, but not in the variable form UVW, but we will try to transform these variables in the form of stream function, because for two-dimensional flow, use of stream function gives us one advantage, that continuity equation upon the use of stream function is by default satisfied. So only I need to solve a momentum equation, and whenever we solve the momentum equation, then also my two variables u and v, like component velocity in x direction and component velocity in y direction, can be written in the form of a single variable, which is a stream function. Okay, so that is the advantage of using the stream function. So first thing is, our majority of these spherical situations will be of axisymmetric nature, so which can be approximated as a two-dimensional flow situation. And for two-dimensional flow situations, we have this important advantage, that continuity, if we use stream function, that continuity equation is by default satisfied, and momentum equation, which is involving variables u and v, these are clubbed together into a single variable psi. Is this one clear? So let us briefly recapitulate. So if I have a two-dimensional flow field in Cartesian coordinate system, then my u becomes del psi by del y and v becomes minus del psi by del x, where psi is nothing but a scalar function. And upon using this field, I can simply write my velocity vector as I times, in place of u, del psi by del y, and in place of v, minus del psi by del x. So this is my complete velocity field. Okay. Now, when we write this one, another important term which also comes into analysis, that is called as actually vorticity. So this zeta symbol over here is nothing but representing the vorticity field. And from our fundamental fluid mechanics understanding, we know that vorticity is nothing but curl of a velocity vector. Okay, and if I am saying that I have a Cartesian coordinate system and I am having a two-dimensional field, then this curl of velocity vector will give me only component of vorticity in the perpendicular plane to xy, so that is nothing but z direction. So that's why this is written as, and vorticity also we know that it is nothing but 2 times of rotation. So omega z is nothing but representing over here the rotation of the fluid medium. So 2 times of omega z, and this k is representing that we are considering only the z component of the vorticity field. So what I can say over here, that this vorticity, though it's a vector field, but for a two-dimensional flow field, it will be resulting in a single component, which I can say simply a scalar component. Okay. Now, value of this omega z, rotation value, if you see from your fundamental understanding of fluid mechanics, then for a Cartesian system, omega z can be written as del v by del x minus del u by del y. Okay, so now if you replace this v with minus del psi by del x, it will be becoming minus of say 1 by 2 is outside, and minus of del square psi by del x square, and if you replace u with del psi by del y, then minus of del square psi by del y square. And ultimately I can write it as nothing but, and when I will be calculating vorticity, then 2 will cancel out. So I will be getting it minus of del square psi by del x square plus del square psi by del y square, which I can represent as nothing but Laplacian of psi. Okay, so that's why I am writing it as minus k Laplacian of psi. Okay, now after this, now comes important thing. So what I have done over here, this is nothing but my, what is this? This is my momentum equation. Okay, so in my momentum equation, what I have done, all the terms which are actually involving u and v, these I have written in terms of the these stream functions. So if I do so, then this is the remaining term and this is nothing but my momentum equation. So that is the advantage. Now why I am only writing momentum equation over here, because if I consider incompressible flow situation, for incompressible flow situation, a two-dimensional flow field, my continuity equation will be del u by del x plus del v by del y. If you replace this u with minus del psi by del psi by del y, it will be plus del square psi by del x del y and minus of del square psi by del x del y, which is automatically 0. So it means this is the first advantage which just now I told you, that if we use the stream function, then my continuity is automatically satisfied. So once continuity is automatically satisfied, I only need to convert my momentum equation in the form of stream function. So when I have converted momentum equation in stream function, then this is my final equation, and you can see now in place of variable u and v, now I have a single variable psi everywhere. Okay, now of course when we typically solve a Cartesian coordinate system, so if I consider, say I have a flow over a flat plate where this velocity is entering at u infinity at the free stream. Okay, so what I can say that this velocity is nothing but parallel to the x direction. So this is my u component of the velocity. So I can specify this boundary condition. U component of the velocity can be written as del psi by del y. So del psi by del y equal to u infinity. And I am also considering another boundary condition, that anything which is traveling normal to this plate, so that will be, of course, at the plate I will be having both the conditions, like tangential velocity also 0 and vertical velocity also 0. So that's why here you can see del psi by del y is representing tangential velocity and del psi by del x is representing vertical velocity. Okay, so both are nothing but equal to 0. So it means that this is first nothing but no slip condition at the wall, and second is impermeable boundary condition at the wall. Okay, is this one clear? Now this term is left, del psi by del x. So this term is nothing but at the left boundary. Why at the left boundary? Because at the left boundary my entire velocity field is nothing but parallel to the x component. So if my total velocity field is parallel to the x component, then I will not be having any component of velocity in the vertical direction at the inlet. So that's why del psi by del x at inlet is equal to 0. So first two boundary conditions, now which were in the form of velocity field, I have actually replaced these in the form of the stream function, and these two are at inlet and these two are at nothing but the solid wall. And as my equation has highest order nothing but 4, so this is 1 del square, this is 1 del square, so it means highest order in the equation is 4. So if my highest order in the equation is 4, then 4 boundary conditions will be sufficient to determine the solution. Okay, is this one clear? So now this is nothing but a well posed condition, and now I need to find out the solution of this. Of course, in this particular lecture, what we will try to see, for majority of the cases, we will try to see the starting governing equation and set of boundary conditions, and solution I will give you directly. Why? Because nowadays we have enormous number of techniques available to solve the equation. So if you go through the literature, if you go to the books of mathematics, then you will be finding the analytical techniques for solving these partial differential equations, and if you know the tools of computational fluid dynamics, then you will be able to solve these equations with the help of numerical techniques. So the major important point is correct understanding of the governing equations and the boundary conditions. Okay, other things are nothing but tools which can be utilized to solve. So that's why our major focus will be to understand these equations properly along with the boundary conditions, and then whatever the solution we are having, we will try to understand all the physical interpretation of that particular solution. Okay, so that's why I will not discuss the solution for any problem, complete mathematical details over here. Okay, so that if you are interested, that you can try by your own. Okay, so because if I start discussing the detailed mathematical solution, then we will not be able to cover the content actually which is particularly desired for this course. As far as the solution of these equations is concerned, I pre-assume that analytical solution you will be knowing mostly from the fundamental fluid mechanics course, or many of you who are PG students, they might have taken the courses on advanced fluid mechanics as well. So there also for majority of these actually these solutions are discussed. Okay. Then as I told you that this Laplacian of psi, del square of psi is nothing but my vorticity field. Okay, vorticity is nothing but minus of Laplacian of psi. Now, if I take the assumption of steady irrotational flow, steady incompressible and irrotational flow. Okay, so what do you mean by steady? Means there will not be any time term. Steady assumption already we have considered here. Then incompressible means for velocity we will be having, for continuity equation we will be having divergence of velocity field, and for irrotational we will be having one more assumption that vorticity is equal to 0. So if I consider vorticity equal to 0, then my Laplacian of psi will be nothing but simply equal to 0. Is this point clear? And irrotational flow situations where you can observe in real scenarios, fundamentally any system which is involving the ideal fluid means fluid of zero viscosity, so there we will be having irrotational flow, but that type of situation will not come in physical scenarios. So in physical scenarios what happens, if you have a solid plate, you will be having some boundary layer portion within this plate where you are having variation in velocity, but outside this boundary layer region you are having actually uniform velocity. So it means outside the region away from the solid boundary, sufficiently away from the solid boundary, you will not be having much effect of the much boundary effect will not be coming into picture. So if much boundary effect is not coming, so here my flow will be irrotational and within this flow will be rotational. Okay, is this one clear? Now for this type of flow situations, if I try to solve the stream equation of this stream functions, then ultimately one important point we need to consider that in any flow field, if I have solved the stream function equation and if I plot this equation of streamline, so ultimately when I will be solving this type of equation, what I will be getting? Ultimately I will be getting my psi as some function of x and y. Okay, so if I plot the lines of different constant values of psi, these lines are nothing but called as streamlines. Okay, so if I consider any two streamlines in the flow field, the difference of these two streamlines nothing but gives me the volumetric flow rate for a incompressible flow situation. Okay, so here you can see this in between two streamlines Q1 to 2, whatever the flow is happening. So if you do integral V dot N dA, that comes out to be integral d psi, and this is psi 2 minus psi 1. Okay. And of course, all these things I am recapitulating only from the basic fluid mechanics course. So that's why I need not to go into very detailed derivation for this. Okay, this is just to revise because we will be using all these concepts in the subsequent discussion. Now this was the use of a stream function for our incompressible flow situations. Now if you consider you have a compressible flow situation. So if you have compressible flow situation, then yes.
So what is the meaning that like psi 2 is greater than psi 1 and psi 2?
Yes, so psi 2 is greater than psi 1 means, of course, whenever you will be plotting this function, you will be assigning some value of C1 to this, then only you will be able to plot this. Then again, when you are plotting this another line psi 2, then you will be assigning some other constant C2. So if the value of C2 is greater than C1, so in that case, when I am moving from this direction to this direction, then psi 2 is greater. So difference of psi 2 minus psi 1 will be a positive quantity. So positive quantity means my flow is in the direction of positive direction. Okay. If this difference is coming negative, then it means flow is in the reverse direction. Okay. So typically whenever you plot this type of solution in the form of psi, we have to specify some arbitrary values to the psi. So typically what we do, near the solid boundaries, we assign the value of psi to be 0, and then away from the solid boundary we try to calculate the values of psi, and we try to see that whether values are increasing or decreasing. So if value is increasing, it means flow is towards the right side. If value is decreasing, flow is in the reverse direction to our assumed direction of the flow. Okay. Then second situation is of compressible flow. So in case of compressible flow, what will be happening? We will be having now density also variable with the space. So that's why you can see in continuity equation I am writing, when I am writing del y del x and del y del y, I am including rho u and rho v. Okay. And typically for this type of situation, because the advantage of using stream function is always that continuity should be by default satisfied. So that's why I am using this now, defining rho u equal to del psi by del y and rho v equal to minus del psi by del x. So if you use this type of formulation, in that case, whenever you will be taking the difference between two stream functions, that will be giving you nothing but the mass flow rate. Is this point clear? Now let's try to see another situation. So this is nothing but 2D flow in cylindrical coordinate system. Okay. So in cylindrical coordinate system, what will be happening? This is the system. So in one direction you will be having variation of r, and in other direction you will be having variation of theta. So in r and theta plane, if you have to solve the flow situation, then what will be happening? So of course the continuity equation for this type of situation is this. So if this is your continuity equation, then you have to select your radial velocity to be 1 by r del psi by del theta, and tangential velocity as minus del psi by del r. Then only your continuity equation will be by default satisfied. And in this type of situation, when your domain is like this, your flow rate will be nothing but difference of psi 2 minus psi 1. Okay. Then another situation, this is also in cylindrical coordinate system, but this is a 2D axis symmetric situation. Axis symmetric in which coordinate? Cylindrical coordinate. So here what will be happening, say if you have a long cylinder and this cylinder is having some flow in this particular direction, and the flow is having symmetry about the central axis, like in case of fully developed laminar flow. Okay, so there what you can do, in place of solving the complete three-dimensional domain, you can only solve this much portion, only this much portion. So here you will be finding this plane will be your r direction, and this direction will be your length direction z. So you will be solving the system in nothing but the rz plane. Okay, so in rz plane, this is the continuity equation. So here we have actually angular symmetry. So this is continuity equation, and to satisfy inherently this continuity equation, This is the formulation of radial velocity and the axial velocity in terms of the stream function. Because ultimately these two are to be chosen in such a way so that whenever these are substituted in the continuity equation, actually these are completely satisfying the solution. Okay. Now here what will be happening, if I simply take the difference of psi 2 minus psi 1, that will not give me complete flow rate through the pipe. Okay, that will simply give me flow rate per unit circumference, because we are only solving a single plane of the complete periphery. So that's why to determine the total flow rate, I have to multiply the 2 pi with this. Okay, because this solution is for complete cylindrical rotation. Is this point clear?
सर जो सेकेंड इक्वेशन है उसके अंदर डी थीटा बाई डी डी डेल बाई डेल थीटा वाली टर्म आर
Here?
से पहले
Yes.
तो सर इसमें आर आना चाहिए.
No, it will not come. So what they have done, you have actually already taken the variation of r in terms of the derivative, so that's why which has already come. So this is nothing but further simplified form. So this is correct.
अच्छा, v theta is not velocity.
V theta is velocity in tangential direction,
in tangential.
in theta direction. Okay.
सर पिछले वाले में जो है कि स्टीप जो फंक्शन है u इज इक्वल टू डेल साई बाय डेल वाई, और इसमें लिख रहा है रो u इज इक्वल टू डेल साई बाय डेल वाई.
Yes.
तो यहाँ साई की डायमेंशन चेंज नहीं हो जाएगी?
No, psi is a scalar function. Psi is a scalar function. It can have any dimension. That's not a problem.
तो फिर
The
डिस्चार्ज हो, फिर डिस्चार्ज के लिए अलग हो जाएगा.
So that's why psi, the dimension of psi has changed because of this only. Difference of psi 2 minus psi 1 in this case is giving mass flow rate, and in the previous case it is giving volumetric flow rate. If you see in the previous case, we are not at all concerned about what dimension of psi is having. We are only concerned about the use of psi in such a way so that my continuity equation is inherently satisfied. Okay, and depending upon that selection of psi, I have to see that whether the difference of the psi 2 minus psi 1 will give me volumetric flow rate or it will give me mass flow rate. So once my density is not accounted for, then psi 2 minus psi 1 was giving the volumetric flow rate. Once density is accounted, so of course the dimension of psi has changed, because of which it is now giving me mass flow rate. Is this one clear?
When we find a discharge stream function, the flow must be rotational.
Flow must be?
Rotational.
No. That is, it can be applied for other situation as well. So flow must be irrotational will be applicable once you are talking about the potential function. Potential function. Whenever we take the assumption that curl of velocity is equal to 0, so this is a mathematical situation which can be satisfied if the vector field can be written in terms of gradient of another scalar function. So that is potential function. So potential function will be only defined if my flow is irrotational. So for stream function it can be applied for any situation. Okay. So potential function I will be discussing subsequently. So in between stream function and potential function, this is the difference. Stream function can be applied for any situation, but it will be applicable only for a two-dimensional flow situation. On contrary, potential function can be applied to any situation like for 2D, 3D, but it will be applicable only for irrotational flows. Okay. So then we have another important equation. Why this is important equation? Because this is in the spherical coordinate system. So whatever the analysis I will be discussing in this particular lecture, that will be that we will try to do in terms of spherical coordinate system. Okay, so that's why this is important equation. So let me do one thing. Let me drop this density over here. This is a typo because I am writing stream function in terms of incompressible flow situation. So let me not consider density here. Okay, so this is my incompressible continuity equation for spherical coordinate system. Okay, so this is for spherical coordinate system. Okay, so in this equation if you have to satisfy, so what we are doing again, because stream function will be applicable only for a 2D field, so r theta, And in spherical, we have this advantage that psi and theta direction will be actually identical. So if we have a perfect sphere, okay. So what we are doing, we are writing that equation in terms of r and theta, okay, for again considering the axisymmetric nature of the spherical system. And if you have to solve satisfy this continuity equation, then your radial velocity and tangential velocity should satisfy these particular forms of the stream functions, okay. And of course in this case what will be happening in spherical coordinate system, we will be having one streamline which is just passing through the center of the particle. Okay, so the one line which is just passing through the center of the particle, typically that is assigned the value of psi equal to 0. So once it is assigned with reference to the center streamline, like which is fixed at the origin, so that's why whenever I am writing the volumetric flow rate, I am simply writing 2 pi into psi. Is this one clear? So because psi 2 minus psi 1 is accounted for, because psi 1 we are considering equal to 0 at the origin. Okay. So typically, yesterday I talked about you the benefits of non-dimensionalization. So whenever we solve different situations, then majority of times we also try to consider the non-dimensional form of stream function at the vorticity field. So this is capital psi equal to small psi divided by u naught into L square is nothing but a way for non-dimensionalizing psi, particularly for incompressible flow situations. Okay, and this is a way, so z over here is representing zeta L by u naught. So this is a way to non-dimensionalize the vorticity field. Okay, so what ultimately will be happening, if you consider your momentum equation for two-dimensional flow field, then that momentum equation can be purely written in the form of psi and zeta. And once we have converted equation in the form of psi and zeta, further we can non-dimensionalize that equation in order to write it in the form of dimensionless psi and dimensionless z. Okay, so these two formulations typically we follow for incompressible flow situations. Now let's try to see one by one different situations. So first situation we are considering over here is inviscid flow or potential flow past a sphere. So I have a spherical particle, and over that spherical particle nothing but there can be two situations. Either spherical particle is stationary and fluid is moving over the spherical particle, or second situation can be that surrounding fluid is stagnant and spherical particle is moving at uniform velocity in the flow field. Okay, and in this particular scenario, what will be happening, I am referring to the assumption of inviscid flow. So inviscid flow means viscosity of the fluid medium is actually not accounted for. Once viscosity of the fluid medium is not accounted for, in that case whenever I will be writing the momentum equation, it will be for incompressible flow situation, it will be du by dt equal to body force minus gradient of p by rho. So there earlier used to be one additional term mu into Laplacian of velocity field. Okay, this term is actually 0 because we are not considering the effect of viscosity. Okay, once this is a very simple equation, and this particular equation in differential form is nothing but called as Euler's equation. Okay, if I integrate this Euler equation along a streamline, okay, if I simply integrate this Euler equation along a streamline, then I simply get nothing but my Bernoulli's equation. So if you see what are the assumptions of Bernoulli's equation, if you are able to read the mathematical form of the equations, all these assumptions you can simply take out from this. So first assumption, if you see, we made incompressible. Okay, we have taken out density out of the derivatives, so it means incompressible. Second assumption is from this to yes, second assumption is inviscid flow. Third assumption is because from this point to this point whenever I am going, I have not included the time term. So if I am not including the time term, it means it's a steady flow assumption. Okay, and fourth is I am considering the flow. Yes, flow is automatically, once I have invoked the envisaged assumption, flow has automatically become irrotational. Okay, and third important point is from this equation to this equation I have come once my equation is applicable along a streamline. So it means once I am applying Bernoulli equation between 2 points, I have to consider that these 2 points must lie on the same streamline. Okay, so this is one of the thing which we majority of the time forget, particularly if you consider an airfoil structure. When we study the flow past airfoil, we say that okay, we are applying continuity here, Bernoulli here and here, and we say that one side pressure is high, one side pressure is low. That is not the correct explanation for generation of lift in the airfoil. Okay, so that is one major mistake we make, because we don't consider the assumption of, we don't satisfy the assumption of application of Bernoulli equation along a streamline. Okay, so here you already know that one is pressure term, then second is kinetic head, and third is potential head. So this is as simple. And once we will be using the irrotational flow, so of course the primary feature of the irrotational flow is that curl of velocity field will be equal to 0. Okay. So if curl of velocity field equal to 0, so it means then del cross V vector is equal to 0. Now there is one mathematical property which tells that if curl of any vector field is equal to 0, then that vector field can be written in terms of gradient of some scalar function. So by taking that benefit, what we write u vector as nothing but gradient of phi, where phi is some scalar field. Okay, and if I extend this, then it becomes del psi by del x I cap plus del phi by del y j cap plus del phi by del z k cap. So it means that this will be my u component of velocity, this will be v component, and this will be w component of velocity. So it means phi can be applied for a three-dimensional flow field, but the primary condition is that phi will be only defined when I am considering irrotational flow. So it will be applicable for irrotational flow, and this is typically called as potential function. Is this one clear? Now, what will be happening? If I consider that I have a stagnant fluid medium, okay, if I have a stagnant fluid medium and that particular fluid medium is and in that particle is moving, okay, so in that scenario, or from my continuity equation, now what will be happening? Laplacian of phi will be equal to 0. So this is nothing but coming from the continuity equation. Okay. Then if I consider my momentum equation, so this is now simplified version of the momentum equation, and this momentum equation is now purely written in the form of spherical coordinate system in r theta plane, and this is applicable, and this complete equation is actually written in the form of only psi, stream function. Okay, so basically when we have obtained this simplified version of the momentum equation, this is obtained from Euler's equation. In the Euler equation, steady term we have made equal to 0, okay, and we have made this particular irrotational flow assumption, and what will be happening, that once we will be taking the curl of this particular field, then we will be finding this right hand side will become 0, and ultimately my convective term will take actually this form. Is this point clear? So what we need to do in this momentum equation, first we need to replace all the velocity fields in terms of the stream function, and secondly we need to take the curl of the momentum equation. Okay, so if you take curl of momentum equation, you will be finding in the right hand side you will be having this term, and this term is nothing but equal to 0. So once curl of pressure gradient is equal to 0, so because of that you will be finding that you will be only left with the convective. Okay, and convective term can be purely written in terms of psi function. All are clear with this point? So what we have done, I am not asking you to do this mathematical analysis. Of course, if it is of your interest, you can do it. But I am telling you the procedure, because procedure you must know. So procedure is, in this momentum equation, we have replaced all the velocity terms. Only two velocity terms we will be having. One is in terms of, because this momentum equation I have to write in the spherical coordinate system. Okay, I have to only consider the r theta terms here. So ur and u theta I have to replace in terms of stream function formulation, which I have given in the previous slide. And once I replace with that, and then if I take the curl of momentum equation, then curl of pressure field will comes out to be 0. Okay, so based on that actually I can write it. Fine.
Curl T कैसे लिखोगे? Curl T कैसे लिखोगे?
Sorry, curl.
Curl T कैसे लिखोगे?
Do this mathematically.
Curl of a
Curl of a gradient field is equal to 0. This is a mathematical property, you can try by doing also. Okay. Okay, so now what will be our situation? Our situation is nothing but a sphere, and in this sphere, this is my r coordinate, and this is the reference. Corresponding to this reference, I am measuring my theta coordinate. Okay, I will be solving it in r theta system, and velocity in r direction is ur, and velocity in theta direction is u theta. Okay, and what I have done, I have considered that my sphere is actually fixed, and fluid from the far field, sufficiently far distance from the sphere, is actually approaching sphere at uniform velocity u. Is this one clear? Now what will be happening, this velocity at the far field, if you see, this is parallel to this direction. Okay, and when this velocity will be actually interacting, so what we need to do, once I am using my r theta system, this velocity I have to actually convert in the form of ur and u theta. Okay, so if this angle is theta, then the component of velocity which is in parallel to r direction, that will be becoming ur, and component which is parallel to this, that will be becoming u theta. Is this one clear? So it means my next process will be, whatever this far field velocity I am having, this velocity I have to transform into the form of radial and the tangential velocity. So that is simple geometric transformation from one system to another system. I know the angle, I can simply transform this. Okay, using simple trigonometric relations. Once at this far field, I know that my ur is known and u theta is known. Okay, so once ur and u theta are known, then what I can do? This ur I can write in terms of psi, and this also I can write it in terms of psi. So both these values can be written in terms of psi. If I write both these values in terms of psi, this left hand side is known. Simply I will be able to know the value of psi by just integrating these two equations. Is this one clear? So what I can do, I can specify my first condition, that when r is approaching to infinity. Okay, so it means all these directions are nothing but r directions. So when my r is infinity, it means r is sufficiently away from the sphere. When r is sufficiently away from the sphere, there my velocity of the fluid is nothing but equal to u. Okay, and that use of that u can be done to calculate the value of psi. That's why I am writing when r is approaching to infinity, my value of psi is minus u r square by 2 sine square theta. All are clear with this point? Then what will be happening at this particle? What conditions I told you? At particle, my normal velocity to the flow will be equal to 0. Okay, so or tangential velocity will also be equal to 0. Okay, so if the tangential and tangential cannot be 0 because now we don't have this viscous effect over here. Yes. Okay, so what I will be saying that my normal velocity to this will be 0. So corresponding to this, what is my solid boundary? R is equal to A. At solid boundary, I can specify that my velocity del psi by del r, some function it will be having, this will be equal to 0, and ultimately from there, or ultimately what I will be doing, I will be finding that no streamline is crossing the sphere because flow is not entering from outside boundary to the sphere, and similarly from this boundary also no fluid is entering to this. So it means at the boundary of the sphere I will be simply having one streamline which is just adhered to this. So corresponding to that particular streamline I will be having a constant value of the stream function. So for reference, what we have done, we have set that value of stream function psi equal to 0. Is this point clear? Because no streamline can enter into this, no streamline can come out of this. So ultimately streamline has to be perfectly parallel to this interface, particle fluid interface. So each streamline is having some constant value of the psi. So we are assigning that constant value of psi equal to 0 at r equal to a. Okay. What will be now happening? If you see, what is the order of this equation? 2. So if we simply impose two boundary conditions with the help of, so this is my equation, this is my main equation which I need to solve, this is the momentum equation, and continuity is inherently satisfied. So this is my momentum equation, and for this momentum equation these two are my boundary conditions. Okay, so you may expect some question in the exam that random set of equations are given, you have to identify which are boundary conditions and which are governing equations and what is the reason for specifying these boundary conditions. So that type of explanation you may have to provide. Okay, because ultimately things are being provided to you. You need not to remember anything, you need not to derive. Okay, so that's why you may expect that this set of fields are given, you have to specify that what are the physical relevance for selection of these equations. Is this one clear?
The tangential velocities make it a 0. Tangential velocity.
I have not told that point even. My simple boundary condition, when I explain to you psi equal to 0, the simple interest is no streamline is interfering this. So the situation is not like this that from outside something is entering inside and then crossing this. Okay, and nothing from inside is entering out. So I can specify a fixed concentric streamline around this sphere. So that is what I am actually saying, psi equal to 0 at r equal to a. Velocity's role I have not actually considered, not at all. Because if I have to consider velocity role, then I have to specify boundary condition in a more complex way, that is in the form of del psi by del r and del psi by del theta. So that is further simplified here. Okay. Of course, that will also work if I do that. So then what we have that when psi is equal to, so if you solve this particular equation, previous equation for psi along with these two boundary conditions, you will be finding the solution of psi as minus u 1 minus a cube by r cube r square by 2 sine square theta. So it means that in this equation what you need to do, you need to simply substitute the value of r. If you substitute the value of r, say at this boundary value of r is equal to a, when you move away from this boundary then value of r will keep on changing. So depending upon the value of r, you can plot all the streamlines for this particular flow field. Okay. And then once you know the value of psi, can you calculate radial and tangential velocities? Very easy, because we have simple relation which is nothing but derivative in terms of r and derivative in terms of theta to calculate the radial and tangential velocities if I know the value of psi. Is this one clear? So from there we can calculate ur and u theta. And of course you can calculate the values of ur and u theta at surface. So here you can see u theta, tangential velocity at surface is 3 by 2 u sine theta, and pressure at surface is equal to P naught plus rho u square by 2 1 minus 9 by 4 sine square theta. So how this solution of pressure is coming? Can you tell me how I can calculate the value of pressure? What you need to do, once you know the velocity field, you are knowing the velocity field, you are knowing this position of each point, you need to simply apply the Bernoulli equation to calculate pressure. And velocity field, how you are knowing? You know ur and u theta at each and every point. So if you know ur and u theta at each and every point, ultimately you are knowing nothing but magnitude of velocity vector, and magnitude of velocity vector square by 2g is nothing but your kinetic head. So this kinetic head and potential head, we are knowing that with reference to the coordinate system what is our location in the vertical direction. So I can simply calculate the value of pressure field. So typically if we calculate the pressure field at r equal to a, then my pressure field is equal to P naught, where P naught is free stream pressure condition, plus rho u square by 2 1 minus 9 by 4 sine square theta. So one important physical inference you will be getting over here, that this pressure field is nothing but a even function. What is the meaning of this even function? The meaning is, once you vary angle from 0 to 90, you will be getting some value of pressure, and when you go in these values 90 to 180, there also what you will be finding? Same value of the pressure. So it means pressure in this direction and pressure in this direction will be same. So once pressures are same in both the directions, then what will be happening? There will not be any drag force because of the pressure. So if there is no drag force because of the pressure, so I can say that in this case my form drag is 0. Okay, so form drag is 0. And similarly, what second condition I am saying, that I have not accounted for viscosity. If I have not accounted for viscosity, I am not having any shear effect. So once I don't have shear effect, it means skin friction drag is also 0. So skin friction drag is also 0. So it means that total drag is 0. Can it happen in reality? In reality, we will not be able to see this type of scenario. So this type of paradox, which gives us 0 drag upon using the irrotational inviscid or potential flow field, that is called as D'Alembert's paradox. Is this point clear? So this is nothing but called as D'Alembert's paradox, and I think majority of you, those who have taken course on advanced fluid mechanics, you might have studied there as well. Okay. So whenever we study the flow past spheres, my pressure function comes out to be a even function if I consider irrotational flow field, okay, inviscid flow field. And in that scenario, we find that our total drag force is 0, which will not happen in reality. So in reality, if you have some sphere, of course that sphere will experience some sort of resistance because of the surrounding fluid. Because of that only the motion of the sphere is not accelerating. Otherwise, sphere will keep on accelerating till the infinite velocity. So you can simply consider, say if a small raindrop is coming, and if you consider that raindrop is coming from so much height and it is not experiencing any drag force, then it will come on ground at extremely high velocity, because if it is not feeling any resistance, its downward driving force will consistently keep on accelerating this. Okay, so that's why because of that acceleration, its velocity will keep on continuously increasing. On contrary, in real scenario, what happens? Air is actually providing some sort of drag force. So basically, you can see that if you increase the velocity, then drag is proportional to square of velocity. So drag also increases with the significant amount. And ultimately, when the driving force and the drag force balances, then we get a constant velocity, which is called as terminal velocity. Okay, so if you consider irrotational flow field, then you will be getting zero velocity, which is not true from the practical considerations. That's why this zero drag is called as actually D'Alembert's paradox. Okay, particularly when you solve your compressible flow problems, there you will be finding that for majority of the compressible flow problems, because our Reynolds number or Mach number is actually extremely high, so my boundary layer thickness is extremely small. Once the boundary layer thickness is extremely small, majority of the flow field can be considered simply as a incompressible flow field. Okay, incompressible flow situations, even if we consider the incompressible situation, then also my drag force is not equal to 0 if flow is supersonic. If flow is subsonic, where incompressible effects are dominating, then of course D'Alembert's paradox will be applicable. But once my flow is supersonic, above then Mach number is greater than 1, then we will be having some drag there, even in case of incompressible flow situation. And there, why that drag comes? That comes because of the formation of the shock waves, which lead to discontinuity in pressure field. So in one side of the shock wave we will be having higher pressure, in other side we will be having lower pressure, and in that particular scenario the magnitude of that shock wave imposed drag force is extremely high in comparison to the drag because of the skin friction. So there that actually dominates. That's why for compressible flows, in incompressible flow we are saying form drag and skin friction drag. In compressible flow we have to consider another component of the drag force in calculating total drag, which is called as wave drag. Okay. So now this is the about the solution of the potential flow. Along with potential flow, we can also have another situation, which is also a very simplified situation, that is nothing but called as creeping flow or Stokes flow. So in case of creeping flow or Stokes flow, what happens? Our viscosity is dominant, Reynolds number is very less than 1. So Reynolds number is small. In that case, we will be finding that advection of the fluid term, inertia of the fluid is actually almost negligible. So once inertia is negligible, you will be finding that your term du by dt, which is considering temporal plus advective term. Okay, so temporal, because of the steady assumption, is 0. In this scenario, our advective term will also be equal to 0. Okay, so once I have advective term equal to 0, then I will be having only two terms left. One is minus gradient of pressure, and this pressure also, if I write in the form of modified pressure, then hydrostatic portion is already included in this term. So already subtracted from this term, like body force is already accounted for, then I need not to separately write rho g hv. So then this plus mu times Laplacian of velocity field will be equal to 0. So this will be my simplified version of the momentum equation. Okay. Now here Pm is nothing but P minus P naught minus rho GHV. So rho GHV field is already included in the pressure term. Okay. Now what I can do, I can take the divergence of this particular equation. Once I take divergence of this particular equation, then my right hand side will become 0 and I will be getting that Laplacian of pressure is equal to 0. So this is one Laplace equation for pressure.
So right hand side 0.
If I take divergence of this, then it will be becoming, okay, let me do one more thing. First, let me take the curl of this. Okay. So once I take curl of this, then what ultimately it will be becoming? This left hand side will be equal to 0. Okay. Left hand side will be equal to 0. And in this particular equation, I will be getting curl of mu times curl of Laplacian of u. Okay. So if you take the curl of Laplacian of u, in that scenario, you will be finding your final form can be written in terms of Laplacian of rotation. Is this one clear, or do I solve this further? So basically what will be happening, you will be having I, j, k, this is del by del x, del by del y, del by del z, and then here you will be having del square u by del square and del square. Now what you need to do, you need to first consider I, and then it will comes out to be del q by del y w minus del q by del y square del z of v. Okay. So similarly, what ultimately you can do from this equation, one derivative you can take outside. So if one derivative you can take outside, inside derivative whatever will be becoming, that will be becoming nothing but a rotation vector. Okay, and then rotation vector can be written as Laplacian of square equal to 0. So it means that once you take the curl of this field, then left hand side is equal to 0 and right hand side can be written in terms of actually rotation vector. Okay, and this rotation vector, further we know that if I have to write in terms of stream function, then how it can be written? It can be written minus Laplacian of stream function. So ultimately what I will be getting? Laplace of, or even a fourth order of del operator into psi equal to 0. So this equation is called as biharmonic equation. And this equation is only applicable for creeping flow conditions. But one thing we need to keep in mind, that the order of this equation is nothing but fourth. So if the order of this equation is fourth, how many boundary conditions we need to supply? So we need to supply 4 boundary conditions over here. Do you have lecture? Okay, let me stop at this point. I will discuss then further. And regarding this Laplacian of P, what you can do, you can once again try the divergence of this field. Once you will be taking the divergence of this, inside you will be getting your continuity equation for incompressible flow in the right hand side. So that continuity equation for incompressible flow can be substituted directly equal to 0, and then you will be getting Laplacian of P is equal to fine. Okay, so further we will discuss in the next class then.